Now we are going to see the introduction of complex numbers, which is the very first module of Engineering Mathematics 1 for the first year engineering students. My name is Bhuma Devi. Okay. The complex numbers. The shortest path between two truths in a real domain passes through a complex domain. The example we can take, the power through which the information is passing in the real time, that is a very good example for the complex domain. For example, the teaching learning process itself, if you are considering, the educator is starting the lecture from the real domain, and the communication medium, the Google Meet, which we are having, it's a complex domain, and the learners, which you people are learning from the real domain, is a very good and the real example for this. So the complex numbers are very important for all the technological aspects. The learning outcome. What are the things that we will be learning at the end of this module? After completing this chapter, the learners will be able to write the expansion of sine n theta and cos n theta in terms of sine theta and cos theta and its powers. We can write the expansions of sine to the power of n theta and cos to the power of n theta in terms of sine n theta and cos n theta. All these expansions, by applying De Moivre's theorem, we can write. The complex numbers are widely used in science and technologies as in the distribution of alternative current and the force vibrations in dynamic system, image processing, which is the latest application of complex numbers, especially in the medical image processing. It's a very wide application that we are having. The definition of the complex number. A number which is in the form of x plus iy, where x and y are the real numbers, and I is nothing but your square root of -1, means -1 can be written as I square, is called a complex number. So in which x is called the real part of the complex number and y is called the imaginary part. Generally, we can denote the complex number as z. Z is equal to x plus iy is called the normal form, otherwise Cartesian form of the complex numbers. If x is 0, then the complex number is purely imaginary. If y is 0, then the complex number is purely real. If z is equal to x plus iy is a complex number, its complex conjugate can be represented as z bar, which is x minus iy. The geometric representation of the complex number, any complex number z is equal to x plus iy can be represented as in the form of p of x comma y in the xy plane, which is known as the Argand diagram. And this diagram in the x-axis is the real axis and y we can call it as the imaginary axis. What are the algebras of complex numbers that we are having, that we will see? If z is equal to x plus iy and z1 is equal to a plus ib, if you are taking the two complex numbers, then the addition of z and z1 can be written as the summation of real parts, which is x plus a plus I into summation of y plus b, which are the imaginary parts of the respective complex numbers. The subtraction also the same way we can do it. We can subtract the real parts, which is x minus a, for z minus z1 plus I into y minus b, which is nothing but the imaginary part of z minus z1. The multiplication part also we can do. Z into z1 can be written as x into a minus y into b plus I into x into b plus y into a. So division part also we can do it, z upon z1. For that we are supposed to multiply and divide by the conjugate of the denominator part in order to bring the real number in the denominator, so that comfortably the numerator can be written as in the form of real and imaginary part. So multiply and divide by the conjugate, which is a minus ib. So when we are doing that case, we will be having xa plus yb plus I into minus xb plus ya upon a square plus b square. A distinct form of complex numbers, we are having the Cartesian, otherwise rectangular form, which is z is equal to x plus iy, which is called Cartesian form of the complex number. And the polar representation, which is nothing but z is equal to r into cos theta plus I sin theta, which is called the polar form of the complex number, in which x can be written as r cos theta and y can be written as r sin theta. And we are having the exponential form, which often we will be using throughout this chapter, which is e raised to I theta, which is equal to cos theta plus I sin theta. It's called the exponential form of the complex number. Then its conjugate can be written as e raised to minus I theta, which is cos theta minus I sin theta. From this, when we are adding the above two numbers, we will be getting cos theta as e raised to I theta plus e raised to minus I theta by 2. When we are subtracting these two terms, and sin theta can be written as e raised to I theta minus e raised to minus I theta upon 2i. We will be using in the expansion part and the later part of the module number 1, these two expansions. And the polar representation that you can see, x and y, and where theta will be the angle and r is nothing but square root of x square plus y square plus y square. You will be having it, that we will see now. The binomial expansions is very important for finding out the expansions of cos n theta and sin n theta. There are two simple binomial expansions that we are supposed to use it, which is a plus b the whole power n, which is nc0 to a to the power of n plus nc1 a to the power of n minus 1 b plus nc2 to a to the power of n minus 2 into b square plus etc. up to plus ncn b to the power of n. The same way we are having a minus b the whole power n, in which the sign of the terms will be alternatively positive, negative, positive, negative. It depends upon the power and depends upon the terms which we are having a minus b and the n, the expansion will come. So in order to find out the coefficients of these expansions, we are supposed to use the Pascal's triangle. The coefficients of the binomial expansion can be found using the Pascal's triangle, as I told you right now. The triangle, it says like this. The triple one is a triangular form that you are supposed to consider. Suppose the n value is 2, then the corresponding coefficients, the combination coefficients will be 1, 2, 1 means in this case, the middle term 2 we are getting by adding the previous row 1 plus 1. The same way for the third order, if you are considering, that is 1, the beginning and the last coefficient will be 1, 1. And the in between term that you have to sum up with the previous row and you have to get the values. So in this case, for the third order, 1, then 1 plus 2 is 3, and 2 plus 1 is 3, and 1. The same way for fourth order, fifth order, till ninth order we can write and keep it ready. And we are supposed to remember and we are supposed to know how the coefficients are coming. That is, it is the starting point is also 1 and the ending point is also 1. The in between terms we are supposed to get it by adding the corresponding two elements of the previous row. That we have to remember. The modulus and the argument, otherwise amplitude of the complex number, let z is equal to x plus iy be any complex number, then its modulus, generally we denote it by modulus of z, which is equal to r, which is can be written as square root of x square plus y square. The argument, otherwise the amplitude of the given complex number, can be written as theta, which is tan inverse of y upon x. Depends upon the positions of the complex numbers, the amplitude values will be changed. Means case 1, if you are considering, when z is equal to x plus iy is a first quadrant where x and y values will be greater than 0, z can be represented as x plus iy, and the corresponding imaginary part is y, corresponding real part is x. So modulus, as you know that you can write, the basic thing behind this finding out the modulus is Pythagoras theorem, that everybody knows, that the modulus of z is equal to r is equal to x square plus y square. Then the argument of z can be written as theta is equal to tan inverse of modulus of y upon x. That means a positive value we are supposed to consider. So the same way for case 2, we have the same way, the theta which is lying in the second quadrant, that we can consider alpha as one of the angle. So according to the information that we can find out, in which r is equal to square root of x square plus y square, as you know, z always we will represent as x plus iy. Then the argument of z, which is alpha as far as this case is concerned, can be written as tan inverse of y upon minus x, because we are having minus x. Because in the second quadrant, the x value will be minus. So we can write pi minus alpha as theta, which is in the second quadrant. The same way for the third quadrant also you can consider, that is alpha is the same thing. The formula is whatever we have written in the previous two cases, the same way we are supposed to write it here also. The argument alpha is tan inverse of minus y upon minus x, whereas we are supposed to take only the positive value. That means pi plus alpha is equal to theta, which is in the third quadrant. The same way for the fourth quadrant, if you are considering, the theta is this and the alpha is, as you can see in the diagram. The case 4, if it is z is belonging to the fourth quadrant, but modulus will be same, square root of x square plus y square, and alpha degree can be written as tan inverse of minus y by x. But 2 pi minus alpha, you can write it down as theta. The properties of complex numbers we will continue. with z is equal to x plus iy and z bar is equal to x minus iy, then the real part of z can be written as z plus z bar upon 2. Imaginary part of z can be written as z minus z bar upon 2i. And when we are adding the whole bar, which is z1 plus z2, the whole bar is nothing but z1 bar plus z2 bar. The same way, if you are dividing z1 upon z2, the whole bar can be written as z1 bar upon z2 bar. The same way you can write it down for the multiplication purpose. The modulus of z1 into z2, the whole bar can be written as modulus of z1 bar into modulus of z2 bar. The argument of z1 into z2 can be written as argument of z1 plus argument of z2. Same way, we are taking the modulus for z1 upon z2, which can be written as modulus of z1 upon modulus of z2, and the argument of z1 upon z2 can be written as argument of z1 minus argument of z2. Whenever the multiplication is coming, the argument should be added. Whenever the division is coming, the argument should be subtracted with each other. That will be, you will be seeing in the exponential representation of the complex number in a convenient way. The problem number 1, find the modulus and argument of the following complex numbers. For the first subdivision, the modulus of half minus I root 3 by 2 can be written as, here in the place of x we are having half, in the place of y we are having minus root 3 by 2. By applying the formula for modulus, square root of half square plus minus root 3 by 2 the whole power 2, which if you are simplifying we are getting as 1. The argument, as you know, the tan inverse of y upon x, we will have it. In this case, y value is minus root 3 by 2 and x value is 1 by 2, which is nothing but again tan inverse of root 3, which is again minus sign we are having. So minus pi by 3 will be the answer for this. So which can be further written as the theta value in the fourth quadrant, which is 2 pi minus pi by 3, which is equal to 5 pi by 3, you can say. Otherwise, you can conclude your argument as minus pi by 3 itself. So if you want to represent us in the form of positive way, then 2 pi minus pi by 3 you can do and you can represent it. So modulus of the second subdivision and the argument, it goes in this way. First of all, we are supposed to simplify the given complex number because we are having 3 distinct complex numbers, 2 in numerator, 1 in denominator we are having. So the multiplication part you are supposed to complete in the first step for the numerator part, which is 19 plus 9i upon 3 plus 2i, we will have it. So we will multiply and divide by the conjugate. Again, we will multiply the numerator part. So if we are doing in that way, 75 minus 11i upon 13, we will have it. So now, again, the modulus formula, the new x is 75 upon 13 and y is minus 11 upon 13. Apply the formula for modulus, square root of x square plus y square, which is nothing but in this case square root of 34. Then the argument of the simplified complex number can be written as tan inverse of minus 11 by 13 upon 75 upon 13, which can be written as minus tan inverse of 11 upon 75. So in this way, we can find the modulus and argument in a convenient way. The problem number 2 we will discuss right now. If Z1 and Z2 are any two complex numbers such that their respective modulus of z1 plus z2 and z1 minus z2 are equal. Prove that the difference of the amplitude of these two complex numbers is pi by 2. Means the tan inverse of whatever the term we are getting, that we are supposed to get it as pi by 2. With the given information, you can write down z1 as x1 plus I y1 and z2 as x2 plus I y2. Since the modulus are same, we are going to consider that modulus of z1 plus z2 is equal to modulus of z1 minus z2. By simplifying this particular modulus, what expression we are getting, that will be helping us to get the amplitude part, which implies that just we are supposed to write down the formula for modulus, and for a convenient we can square on both the sides. So in that way, if you are doing the x1 plus x2 the whole square plus y1 plus y2 the whole square should be equal to x1 minus x2 the whole square plus y1 minus y2 the whole square, we will be getting if you are simplifying the previous step. Expand according to your formula using a plus b the whole square, otherwise a minus b the whole square term. So like this, if you're expanding and if you're cancelling the like terms of the equations on both the sides, then we will be getting the simplified form as 4 times of x1 into x2 plus 4 times of y1 into y2 should be equal to 0. By taking 4 as a common factor, we will be getting here it as x1 into x2 plus y1 into y2 is equal to 0. So that's what the expression which we got it from the given information, which is modulus of z1 plus z2 is equal to modulus of z1 minus z2. So this we have to keep in our mind to get the final result, which is a difference of the amplitude of the given complex number should be pi by 2. This we have to keep it in our mind, this particular step, which is x1 into x2 plus y1 into y2 is equal to 0. Argument of z1 minus argument of z2 can be written as tan inverse of y1 upon x1 minus tan inverse of y2 upon x2. So if you are applying the formula, the simplification part for tan inverse of this can be written as y1 minus y1 upon x1 minus y2 upon x2. The whole thing upon 1 plus y1 y2 upon x1 x2. Simplify the term which you're having within the bracket. So when we are simplifying this case, we are having tan inverse of y1 x2 minus x1 y2 upon x1 x2 plus y1 y2. But we got the denominator part as 0 by the given condition modulus of z1 plus z2 is equal to modulus of z1 minus z2. So denominator, it becomes 0 in this expression, which is tan inverse of infinity. Anything upon 0 is infinity. So tan inverse of infinity, which is pi by 2. Since I told you that step which we have considered from the given condition. So the argument of z1 minus argument of z2, which is the difference between the amplitude, we are getting here it as pi by 2. So this is all about your introductory part of complex numbers.